So now another reaction is the oxidative cleavage of alkenes. So now this one is going to oxidize our alkene, but it's also going to break the molecule apart. So if I take this kind of unsymmetrical alkene and treat it with ozone first, and follow that up with zinc and water, what happens in this reaction is that this bond gets cleaved in half, and both sides of this get oxidized up to a ketone. So the easiest way to think about drawing it is to draw it the way that it was originally, but you don't draw in the alkene bond, right? Right here's where the alkene bond was. And instead of drawing in the alkene bond there, both of those sides are now carbonyls. So this top one ends up being a ketone because there were 2 carbon bonds on it originally. The bottom one ends up being an aldehyde because there was only 1 carbon bonded to that in the original structure. So as always, the alkene has electrons. These electrons are going to come out to one of the oxygens, which is going to push the pair from the pi bond onto this central oxygen. But then this oxygen has a lone pair of electrons and a negative charge, and that's going to come in and attack the other side of the molecule. And that makes what's called a molozonide intermediate. And then without drawing the mechanism, that rearranges into an ozonide. And this is sort of a complex mechanism again, because what happened here is that one of these oxygens inserted between the 2 carbons that were bonded to each other before. And then from that stage, when we treat it with the zinc and water, then this all breaks apart and both sides get oxidized up to the carbonyl to give the final product. So you can see that this zinc and water is used to reduce this ozonide that forms. So this one's called a molozonide, which rearranges to form the ozonide, which gets cleaved by the zinc and water to give our 2 carbonyls. You can also do oxidative cleavage of alkynes in the same way. So you just cut this molecule in half, and all those carbon-carbon bonds get oxidized up to carbon-oxygen bonds. So what happens then is one side ends up being carboxylic acid. In this case, the other side is just 1 carbon, and that gets oxidized all the way up to carbon dioxide. So oxidation of alcohols works well with primary alcohols, and it works well with secondary alcohols, but they do not work at all with tertiary alcohols. And the reason why is that there is no hydrogen on this carbon that's bonded to the OH. Here I have 1 hydrogen that I can replace. Here I have 2 hydrogens that I can replace. But here I don't have any hydrogens on that carbon. And so that's going to make the tertiary alcohols not oxidizable in the same way that we can oxidize the primary and secondary alcohols. So let's start with secondary. So I can take my secondary alcohol and I can treat it with potassium dichromate, sulfuric acid, and water. And what that does is it oxidizes this alcohol up to a ketone. I can do the same thing with CrO3. Usually we'll write CrO3 and acid. That oxidizes this up to the ketone. Now, how these work is typically about the same. So I'll take an example and draw it for you. So who has electrons and who wants them? The oxygen has electrons. The chromium wants them. One of these bonds will break and go out onto oxygen, give me an intermediate. And now, as we've seen before, one of the lone pairs on this oxygen that has a negative charge will come and grab the proton, who has a positive charge, pushing this electron pair out onto oxygen. We've seen that mechanism happen several times, sometimes within the same molecule or sometimes from a different molecule. We did it with pyridine a few times. And so this molecule now, this is called a chromate ester. And now from the chromate ester, what happens is we have to have a water molecule around, which comes by and grabs a proton from the carbon that oxygen is bonded to, which pushes this electron pair up here to form a new carbonyl bond, and pushes this electron pair out onto chromium. So we get our new carbonyl bond, we get H3O+, and the chromium compound gets protonated as well. Like this, which is now chromium 4+. Back here, this is chromium 6+. So the chromium is reduced, and in the process, our carbon is oxidized. Now there's a milder oxidizing agent, and that's pyridinium chlorochromate that we talked about before, PCC. But PCC will still oxidize this up to the ketone. So at this point, it doesn't make any difference with a secondary alcohol whether we use potassium dichromate, chromic acid, or PCC. They all work the same. Let's see what happens with primary alcohols. So if I treat a primary alcohol with chromic acid and water, what happens is it gets oxidized all the way up to carboxylic acid. So this is a strong oxidizing agent. If I take sodium dichromate, which is also a strong oxidizing agent, the same thing is going to happen. However, if I have a weakened oxidizing agent, like PCC, now I can get this to stop at the aldehyde. And of course, what's great about that, again, is that what do organic chemists want to do? They want to be able to control everything. And so now I can take my alcohol. If I have a primary alcohol, I can turn it into carboxylic acid if I choose to, or I can stop it at the aldehyde if I choose to.